Today talking about chromatography.
Just one more brief announcement. The D&D Club is canceled today. Again, the D&D Club is canceled.
Oh, no.
I was going to go to that.
Okay. Chromatography then is a way that we can separate liquid mixtures from one another. It there's a couple different ways of doing this. There's three that we're going to talk about. And it's going to base it on polarity differences. So we're looking at polarity here. And the polarity differences are sometimes considered solubility as well, which is what we're going to talk about the second part of today. So first of all is paper chromatography. This is the one that you might have done in elementary school with the Skittles and coffee filters. It's kind of a classic, like elementary school kind of lab. Then layer chromatography and column chromatography. Honestly, I have never done these two, and I have never seen them on an AP exam, but they're listed as parts of things that you guys should know, so they could potentially end up there. All right. Like we said here, this is the one that's most commonly seen in AP Chem, and there's usually a question on there in some fashion regarding this. Okay. So when you do paper chromatography, you always start, it's typically an ink that you're working with. Like I said, it could be an ink dye, something like that. Like on the, you know how your M&Ms have different colors? Those are food dyes. If you add food coloring to stuff at home, your mom might have little squirt bottles that has food coloring in it. Sometimes they're pastes. Just depends on how they get them in. So you will typically draw a line in pencil near the end of the paper, so you'll note where that is. Then you'll put a drop on that line of the dye, and then you're going to place that paper in a sealed container with a shallow layer of the solvent. You don't want the solvent to actually touch the dye. So this shouldn't be submerged in that. Just the tip of it should be there so that it can wick its way up, kind of like a paper towel. If you've ever seen a paper towel on a liquid where it wicks up through the paper towel, okay? That's where you want to put it. And then you let that continue to climb up. And you want to pull it out of the solvent before it reaches the end here, because you need to see how far these dyes travel, and you're going to measure that, okay? So you're measuring the height of the leading edge of the solvent of each dye, and you come up with a calculation, okay? So when you analyze these, you will mark where you stopped when you pulled it out, where that solvent was when you pulled it out of the water, and you will have your baseline here, and you're going to measure from that baseline to the leading edge of the solvent, and you subtract. That becomes then your RF value. Okay. And you're looking to see how that's going to react to this paper. Okay. Paper tends to be slightly polar. And then you look at, you look at the solvent and what solvent you had it in. So for example, if you had this in water, water is polar. So the more polar dye is going to climb higher up on that paper. If you had something like benzene in here, then the more polar solvent would stay towards the bottom, and the less polar would climb higher. So it depends on what the solvent is as to how the dye is going to interact. So when you look at this, they commonly have different names for different parts of this. So the stationary phase is the paper. The paper's not moving, so that's why they call it stationary. The solvent then is moving, and where you pull it out of the container, that is called the solvent front. And then you're always going to have a baseline. So polar water will have polar samples travel further Nonpolar samples will travel shorter. And then if you put it in a nonpolar solvent, then that is reversed. All right. The next type is thin layer chromatography. So thin layer chromatography is similar to paper chromatography, but this it's kind of almost like a glass slide or something, okay? Or they're talking about a thin piece of plastic. Either way, on top of that, they're going to have something like silica on there, and that is extremely polar, like stupid polar, okay? So because of that, when you are doing this, you can watch and see how far the materials climb with this, but you have to use a solvent that will fluoresce under UV light. So they're going to put this in a solvent and see how it moves. Then you use UV light to see how far these things are moving. So this is pretty typical with like amino acids and stuff in biology. We don't typically do this one in chemistry, but you'll see it sometimes in bio. Did anybody do this in AP bio?
Did you have when did you have AP bio?
Okay. So thin layer chromatography, the same compound will move at the same rate relative to the solvent in different trials. Different compounds will have at least slightly different polarity to other compounds, so the RF factor will differ between compounds. The more nonpolar the sample, the further it's going to travel. The more polar it is, the less it's going to travel, because it's going to be more attracted to the material, like the paper, like we talked about paper. Well, this is the silica. So that silica is going to kind of hold the polar stuff back. The nonpolar just takes off. And then you can compare those RF values then. Okay. All right. So then we have column chromatography. Typically, they're going to put steel wool down in the bottom here to keep the material from just falling through this column. Then they're going to put something that's polar in there and a mixture. And the mixture then will come through here and start to get separated based on its polarity. And what they do is they pull the stuff out that's coming out, and every time it kind of changes color or changes substance, then they start analyzing that different part. Okay. Distillation is another way to separate liquids, and that's based on the different boiling points. And we talked about that briefly yesterday, so you can go back and watch that video from yesterday if you'd like. Applications of distillation. This is how they separate fermented beverages. So alcohol. Have you ever heard of like moonshiners and their stills? That's where they get it from. Okay. So if you watch anything about moonshining or anybody that's making their own liquor, I'm not talking about wine. I'm talking about hard liquor. This is how they separate that out. Okay. Salt water. And then refineries, this is actually, they get crude oil in from the oil fields, and they will use the different boiling points to pull off the different parts of the crude oil and separate it out for use for different applications. So here is like some examples of some of the paper chromatography. Okay. All right. So you get the idea of that one, right?
Yes,
Okay.
ma'am.
So now I want to see if I can find his column chromatography.
Do you have a Tracy spreadsheet?
Huh?
So-
It's schools. Um,
I have
wait. Oh, wait. It may not work. Yeah, it will. It should work. Okay. We have to check it as part of our advisory. So that's what that looks like.
That's the
which we have. Okay. Okay. Does that make sense then?
Sure.
And you guys have been able to see kind of what those look like. That's what I wanted to get at. Okay. Okay. Here's 310. Here's where I want to start. All right, so solubility. Solubility describes the extent to which a solute will dissolve into a solvent to form a solution. If a lot of solute can dissolve, it's described as being highly soluble. If very little dissolves, it's slightly soluble. And if none dissolves, it's insoluble. And we'll learn more about, we'll actually assign that a quantitative value when we get into unit 7, I believe. We'll talk about the solubility based on a number. Like you can look at a number and tell if something's soluble or not. But we can't talk about that until we get into unit 7. So this stuff is going to come back. Okay. Yep. So water is a common solvent. Because it has the ability to dissolve a lot of different things because it's polar. Okay. So water is extremely polar. It has 2 sets of those lone pairs of electrons. It ends up being, it has that highly electronegative oxygen on there where the electrons kind of stay in this region of the molecule more than this region. Okay. When an ionic solid is dissolved in water, so we're going to put this solid in water, okay, the water molecules will start to pull that apart. The positive ion will get surrounded by the negative side of the water molecule, and the negative ion will get surrounded by the positive end of the water molecule. Make sure that if you're drawing a particle diagram, that if this is in a 2-to-1 ratio, as this equation would indicate, or chemical formula would indicate, that you make sure that you draw the right number of ions within that. Okay. You wouldn't want to have 4 of these and 4 of these. You would always have 4 of these and how many of these? 8. Okay. Now, in this situation, we have water molecules left over. So what would this solution be considered? We talked about that briefly yesterday. Unsaturated. Okay. If we have a situation where all of those water molecules are surrounding these and we have some of this left over down on the bottom and it's all together like this, then that would be saturated.
Super saturated.
Well, we're not going there. Okay. So water can also dissolve non-ionic substances as well. So water is attracted to the polar part of, for example, acetic acid. So acetic acid has this OH hydroxyl group at the end here. That grouping here is going to create hydrogen bonding. And so because of that, it's going to be attracted to the water molecules. So this alcohol, or I'm sorry, this acetic acid then, this acid is going to be dissolved in water. Not all substances can dissolve in water. You can think about like dissolves like, but don't write it down on your paper.
Will they mark it
It's
wrong?
banned.
They hate it. Like, just don't do it.
But will they mark it wrong?
Well, you can write it down, but you need to go on and further explain it. So don't waste your time writing it down because you're going to have to explain it anyway. Don't write it down. Okay. You guys can rebel against the authority every once in a while, and that's fine. But don't choose this as your time to, don't make this the hill you die on. Okay. Metaphorically speaking. All right. Not all substances can dissolve in water, like I was saying. Okay. Typically, things that are polar will dissolve with things that are polar, and things that are nonpolar will dissolve with things that are nonpolar. We talked about that yesterday, and how if water is attracted to other water molecules, it's going to be more attracted to other water molecules than it would be to a nonpolar substance that comes in here. And that's why they separate into different layers. There are 3 steps that have to occur in order for a solution to form. The solute particles have to separate. So if we go back and look at this guy, this stuff here has to separate from one another. What's going to cause that separation? What's going to pull this apart?
The water.
Right, the attraction from the water. Well, the water is attracted to other water molecules, so that also has to separate. And then the water has to surround those ions. Okay? So the solute particle has to separate, the solvent particle has to separate, and then they come back together. So solute separates. Think about magnets. Okay? So if you think about this in terms of magnets, if you pull 2 magnets apart, does that take energy?
Yes.
Okay? So that's the first 2 here. But you bring those magnets back together, and what happens? They stick together. Okay? Did that take any energy to get them to go back together? No, they just kind of, it happened. Okay? And you're going to end up with energy released in that process. Now, if this is greater than this, it's going to feel cold. If this is less than this, it's going to feel warm. You got more energy released than was required. Okay. And yesterday we talked about diluting acids down. When you're diluting acids, this is what you're doing. Okay. And there's so much energy released in that process that it can be very dangerous. So the amount of energy needed for each step on the IMF, it depends on the IMFs of the material. The stronger the IMFs, the more energy is going to be involved. Polar substances will dissolve into polar substances. Nonpolar substances will dissolve into nonpolar. Nonpolar substances do not dissolve into polar, and vice versa. There's not enough energy released in the last step to negate the energy of the first 2 steps. So when 2 substances can mix together, they're said to be miscible.
And when they cannot, they're
Immiscible.
like oil and water. And why did we say that was, everyone? You know.
Doesn't have to do with density. I can tell you that.
No, it's because one of them is polar.
Exactly.
The water actually itself and not allow the water to be part of the party. Please, I know the party. I know. Thank you. Okay.
IMFs.
NaCl. Yeah, it is.
I honor.
Types of atoms. Okay, so CH2O. That has.
Where's CH2O? Oh, down here? Oh.
Yeah. Double bond. No hydrogen bonding. That's, you did? Did you know I'm not an elevator?
What else here?
I actually didn't know.
LDF. No hydrogen bonding.
What about this guy?
Tiny MM.
Which guy?
CO2.
Yes,
So what are the IMFs?
LDF.
What about this guy?
LDF. Boom, that's it.
What about this guy?
LZ,
What about this guy?
all of them.
HB, DD,
Dipole, hydrogen.
LDF. Oh, what?
Boom.
Okay, so what's going to mix with what?
Water.
It-
Light with light.
Okay, so NaCl, what's it going to mix with?
Water.
Water. Okay. What about this guy? Hexane. This guy.
Bottom is
Water.
water.
All right, there you go.
Yeah, good. Okay. Next.
Now-
we're done.
Does this guy, is he soluble in water?
Yes.
Yeah. Okay. So slightly soluble in water. That's why your pop has carbonation in it. But your pop also goes flat pretty quick, right?
I love flat soda. No, I do. I only drink Sprite that doesn't have the bubble.
Yeah, I don't hate carbonation.
Yeah, man.
So
I agree.
I only like the lemon part. I don't like the actual carbonation stuff.
Drink lemonade.
but remember they put that under pressure and that gets this to dissolve better. Okay.
That's why I like explode.
Yeah, if you go.
That was loud.
Okay. Good.
All right. So there you go.
Can I use the restroom?
Yep.
No.